Plastic moment is an extremely valuable number for us to keep track of when we're doing a steel design problem. Let's look at a W12 by 72 made of A992 steel, and we are going to compute the plastic moment, MP, in both the weak and the strong axis. Now, the plastic moment is given to us by the equation MP is equal to Fy times Z, where Fy is the yield stress of the material, so we are dealing with Fy equals 50 KSI in this case, and then we are dealing with Z. Now, Z is a value that we have for both the X and the Y direction, and we'll use these accordingly for when we're doing the weak and the strong axis. We can find these values in AISC table 1-1. However, what we're going to do is we're going to calculate it for the strong axis by ourselves and then compare that with the AISC value, and then we will go back and we will do it again using the we'll use the table for the table values for both of these equations, but I just want to make sure you understand how to calculate it. So Z is given to us, as I have written here, A, which is the cross-sectional area of the shape, times A over 2, little a over 2. And A I have written out here. I'll write it again as I'm writing through this, talking through this, but it's going to be equal to the depth of the full section minus 2 times Y bar, or Y bar is kind of unique to explain here. There's probably a better way of writing this, but I'll explain it right here. So if we have our I-beam right here, we can split this in half, and we have 2 equal cross sections. The value of Y bar that we're looking for is the distance from the outside edge of the flange to the centroid of this top half. So we'll just say it's right here for the purposes of this. But how do we go about this? Well, it turns out if we have a W12 by 72, half of that would be a WT 6 by 36. And if we want Y bar, that's a value we can get from table 1-8 in the manual. So if you're gonna go, you'll find that Y bar for a WT 6 by 36 is equal to 1.02. So we can calculate A. We know that D is equal to 21.1 from the manual. And then we have small a over 2 is going to be, oh, no, I'm doing the wrong thing again. As I just said, or as I meant to say, D is equal to 12.3. And then we're going to subtract 2 times that Y bar value, which is 1.02. That's going to give us 10.26. We can now go and find this is our ZX value. 21.1 is our cross-sectional area. And then 10.26 divided by 2 is going to give us 10.761. No, pardon me, that's incorrect. It is going to give us 108.243. And if you go look at the manual, ZX is 108. So we found the right value, so that's great. Now, if we want to do plastic moment in the X direction, we just need to say Fy times Zx, and that is going to be 50 times 108. So 50 times 108 comes out to be 5,400. And let's do a sanity check on our units here. Z is in inches cubed, and this is KSI. So that leaves us with kip inches, which is correct. But normally the way this is going to be characterized is 5,400 divided by 12 because we want this in kip feet. And that is going to be 450. So we have 450 kip feet is MPX. Now let's do our MPY. And it's really not that difficult. We're just going to do the same thing again. MPY is going to equal Fy times ZY. Now we didn't calculate out ZY, but we can just go to the table to do it. For a 12 by 72, our ZY value is going to be 49.2. So we have 50 times 49.2, and we can just divide by 12 right now. 50 times 49.2 divided by 12 is 205 kip feet. Now there's an easy-ish way to check this, and we can do that right now. So if we go to table 6-2 in the manual, well, I should clarify this for one thing. So the plastic moment, if you don't know, you should know that it is equal to the nominal moment when and only when LB is equal to 0. So if you have a beam that is fully braced, this is the condition that you will be looking at, where the nominal moment is equal to the plastic moment. And the design tables reflect this. So if I go to table 6-2 in the manual, which is personally my favorite, or pardon me, table 6-1 in the manual, which is personally my favorite one to use for any sort of design problem, we will find that we have, it's a 1272, takes a minute to get there because this table is pretty long, that at an unbraced length of 0, the LRFD design strength is 405. So for LRFD, phi MN was equal to 405, which makes sense because phi is 0.9. So 0.9 times 450 is 405, which means you have the correct answer here. We can also go and we can check in the same table the phi MNY value, and that says 185. That's all the way in the bottom right corner if you hadn't seen it, or bottom left corner of the page if you hadn't seen it. That says 185, so 0.9 times 205, just double check it in our calculators, 0.9 times 205 is 184.5. So that's a quick way to check if you got the right values here. Remember that they're going to be reduced by that phi b factor. I used the LRFD example here. You could also do it with the safety factor if you wanted to do ASD, but I like using LRFD for these problems. I think it works, makes more sense in my brain when I'm teaching them, and it's honestly going to be the more common thing you see when you're working with these problems now. So feel free to mess around with problems like this. They're not too complicated, and they're good practice for the brain. So I hope you guys found this helpful, and if you did, please drop a like and subscribe to the channel, and we'll see you in the next one.